So again, let me try one more time here. Dr. Cosima Eibensteiner.
Eibensteiner, yeah.
Eibensteiner. And she has this great presentation for us tonight on observing nearby galaxies. So over to you.
Thank you for giving me the opportunity to talk about nearby galaxies and why I love them so much. But before I talk about them, I wanted to show you or just introduce myself a little bit and my way. So that's me on the VLA, which is pretty cool. And I'm actually interested in the cold neutral molecular and atomic gas, so gas that you cannot see in a visible wavelength, and nearby galaxies, as the title already said. And altogether, I'm interested in the interplay between the content of this gas and star formation. And so just to show you, I think my accent tells you already that I'm not from here. I did my bachelor's and my master's in Vienna in Austria, where I was born. So that's Vienna here in the Schnitzel. And Red Bull is also from Austria, if you didn't know that. And I did my doctor or PhD in astrophysics in Bonn. And if you know Haribo is from Bonn. And then after my defense, basically 2 weeks after my defense, I moved here to start my postdoc as a Jansky Fellow at the National Radio Astronomy Observatory around the corner. Okay, so the overview of my talk. Well, I will talk about nearby galaxies and how we will observe them. I will focus on the gas that we cannot see in the visible spectrum, so neutral atomic and molecular hydrogen. And I will give a little bit of more information and more detailed information. I will mark this with this icon on the top right of a slide. Especially also, I will highlight some findings of my research. I try to make it really simple, keep it simple. I start with our own galaxy, the Milky Way, which is, of course, here an artistic representation because we are inside of our own galaxy. So this is what we see, and well, there we are. We are around 25,000 light years away from the galactic center. The diameter of the galaxy is around 100,000 light years. We have around 100 billion stars in our own galaxy. This whole galaxy weighs about 1.5 trillion solar masses. And what we are maybe more used to is to see this galaxy actually in edge on, although we cannot see this as well, right? Because we sit inside of the galaxy. What we see here is now the position of the sun, the bulge, a lot of stars, the global gas cluster, the disk, and the stellar halo. And this is the edge-on view in a way. But both of these representations are artistic representations, not real observations. And again, here's the sun. So we see here dust, the galactic center. In the center, we have a supermassive black hole with around 5 million solar masses. And here you can see also the small and large Magellanic clouds, short SMC and LMC. So this is a real observation, by the way. You should be familiar with that, I think. And so I think you already mentioned that today. We thought actually only 100 years ago that the Milky Way is the only galaxy out there. And that was actually the great debate between two people in 1920, Harlow Shapley and Herbert Curtis. So the guy on the right was like, yeah, the Milky Way is all there is. And Curtis said, no, there are a lot of other galaxies out there. And the subject of this discussion is this kind of object. Who does know this object? Yeah, Andromeda, M31. So Shapley said, like, okay, this is actually a spiral nebula. It's part of our own galaxy. And of course, Curtis was right. He said back at that time, it's a whole galaxy on its own. It's extragalactic. So he was right. Only 4 years later, Hubble and others observed Andromeda, a dozen of pulsating stars. So they changed the brightness in a regular periodic fashion. I always have troubles pronouncing this name, but you call them Cepheid variables. Cepheid. So back then it was already known that the time it took them to pulse was directly related to their luminosity. And so if you measure the period, you can then determine how far away they are. And so they measured a distance of about 900,000 light years. I will talk about galaxies that are no further away than 20 megaparsecs today. So what does this mean? 1 megaparsec here as a reference are 3 million light years. So still very far objects, but I call them nearby. So, however, even in 1755, Immanuel Kant, in one of his essays, asked, are nebular external galaxies, so-called island universes? And you see here a drawing of one of these spiral nebulars. Which kind of spiral nebula is that? M51, yes, it's the Whirlpool galaxy. Here you can see it now, very beautiful, captured by the Hubble Space Telescope. So why nearby galaxies? I already told you we are sitting in our own galaxy. And so we need a little bit of a different view. Everything that we already know from our own galaxy, the artistic representations that I showed you, we know because we also looked at other galaxies. And another thing that we have sitting in our own galaxy is it's a line of sight confusion, which means we look at the center of our galaxy, and if we want to see something beyond the center of the galaxy, we have a lot of stuff in between. So it's really hard to find correct distances as well of the gas, for instance, or the stars. So that's one idea why it's cool to look at other galaxies. Also because we have a lot of different galaxies out there. So we have a diversity of galaxies, but also if we look at nearby galaxies that are Milky Way-like, we can dissect them into individual parts. So the spiral arms or the bars, and then look where stars are forming in a statistical manner, and then link back to our own galaxy. So in a way that would then benchmark for understanding galaxy formation and evolution as well, because we study galaxies that are in different phases of their life. Either they're star-bursty, so producing a lot of stars, or they're already dead, where they don't produce any stars anymore. Okay, and so with that in mind, let's travel to one of those nearby galaxies. Can somebody already guess which kind of galaxy that is? It's not M101. It's a Messier object, yeah. Yeah, M83.
Many, 3 million light years or less.
Yeah, so this is now 5.5 megaparsecs.
Wow.
So it's inside like the 20 megaparsec range that I'm looking. And so, of course, this is now in the visible light of the electromagnetic spectrum. We see beautiful arms, a bar-like structure in the center. And all of this pinkish colors represent ionized gas in a way that you see here a lot of star-forming regions. So there, stars are forming. And however, the fuel for star formation is molecular gas. And so you can see here now in the millimeter wavelength range, so longer wavelengths that we cannot see with our own eyes, the distribution of molecular gas. Again, you see it's distributed around the spiral arms, and also a lot of things are happening here in the center. So the pink colors mean there's a lot of gas there. Bluish colors mean there's less gas available. And if we want to even look at the reservoir of gas, so in a way you have a lot of gas in a galaxy that travels in the center of a galaxy, becomes molecular, and then this is the fuel for star formation. And to look at this kind of gas, we need to zoom out a little bit again, because you will see it's super extended, way more extended than the optical disk. So here I show you now the centimeter wavelength in the radio, so really long wavelengths. And this shows you the distribution of atomic gas in this particular galaxy. So for that galaxy, M83, the atomic gas disk is 5 times the radius of the optical disk.
Is the scale of this galaxy about the same power?
Yeah, the optical, yes. And so if our eyes would be able to see this kind of gas in a night sky, which would be awesome, it would appear similar to 9 moons, which is crazy. And so the tools behind all of these are telescopes, of course. So one of these is the ALMA telescope in the Atacama Desert in Chile. Consists out of 66 antennas. And I'm using that to trace molecular gas. So you could do a lot of other things with it as well, but I use it to trace molecular gas. Another telescope, the Carl Jansky Very Large Array, is located in New Mexico. So if you are in New Mexico and have time, spare time, I really recommend you to go there. They offer really great tours for free. So just go there. It's amazing. And then you can also, so I use this for atomic gas, but you can also take then a picture like I did in front of. And another one, which is newer, is the More of Karoo Array Telescope. So astronomers always like acronyms. Is in the Karoo Desert in South Africa. Operates with all of its antennas since 2018. And I use it again for atomic gas. Okay, so why so many dishes? This is now a very basic introduction in radio interferometry. So we want to collect a lot of photons. And so for that, we need a lot of pockets in a way. Those are the dishes that collect the photons. So that's why we want a lot of dishes. And why do we want to have them distributed? So this is me again in front of the MeerKAT telescopes. This is now Cape Town here in South Africa, and here in the desert, a 9 hours drive, which is really long for me, but from the optical, you know that the resolution depends on the diameter. In radio interferometry, the resolution depends on the dishes that are furthest away in your array. And so that we call the distances between those telescopes in an array, we call baselines. And so that is important. You want to have a lot of dishes and also dishes that are distributed across kilometers, few miles. Okay, another galaxy. Which galaxy is that? Say again? No. It's one of my most favorite galaxies. It's here on my phone as well. It's NGC 6946, the fireworks galaxy. Yeah, somebody got it right. This is just, but But if we look now again into one of these regions in a very simplistic way, what we see there is diffuse atomic gas, dense molecular gas, so the fuel for star formation, some stars that already have formed, and then some leftovers, which are supernovae, so when stars die. And all of this is part of the so-called baryon life cycle. So baryons are the fundamental building blocks of the visible matter in the universe. And so we start with a diffuse cloud. So this is the reservoir of gas. That's what I showed you with the atomic gas mostly. This contracts and forms denser molecular clouds, which are mostly molecular and provide the environment for star formation. This indicates how cold or hot it is, and this indicates the density, where you have like a lot of particles here means it's very dense. And with a gravitational collapse, we end up with massive stars, and those guys release enormous energies and then ionize the surroundings. And if the pressure is low enough, gravity takes over and they go supernova. And so with that, they inject the huge quantities of chemically enriched gas back into the interstellar medium. And so this whole process is in a way a recycling of gas in the interstellar medium. So this is now a little bit more detail. I tried to keep it simple, but you can ask me afterwards if you have more questions. So how do we now see molecular neutral atomic gas? Let's start with diffuse atomic gas. We have a hydrogen atom, which consists out of a proton and an electron. And through a spontaneous flip, where the electron changes its flip from parallel to antiparallel, it will emit a photon at a characteristic wavelength of 21 centimeter. And that is the so-called 21 centimeter emission line of hydrogen, or H1. Sometimes throughout the talk, I will refer to it as H1, but I try to stay with the term neutral atomic hydrogen. But if I say H1, that's what I mean. And how do we observe now dense molecular gas? So H2 is the most abundant molecule in the interstellar medium. However, observing it with radio telescopes is very difficult. It needs a lot of energy to get rotationally excited. That means it's really, really hard to observe. Actually, it's not possible with radio telescopes. So what we need to do is we need to take another molecule, carbon monoxide, the second most abundant molecule, which we know where we find CO, we also find H2. So an indirect indicator for H2. And just to represent this in a little bit, in a way, you have the energy level of this molecule. Imagine these are different energy levels. So they're level 0, 1, and 2. And so collisions will lead to an electron getting excited to a higher energy state. So we put now an electron, wait, doesn't work, here, the electron to a higher energy state. It went from 0 to 1. However, it won't remain there for a long time. It's, in a way, molecules, or like these guys are very lazy. They want to be always in the lowest ground possible. And so they will de-excite. And while they do that, they release some energy, a photon. And this has a characteristic wavelength of 2.6 millimeters, which we see then as the CO 120 emission line in our observations. And these other colors here should represent a little bit more denser parts of the molecular clouds. I won't talk about that, but those are typical, even more exotic for extragalactic people, more exotic molecules: hydrogen cyanide, HCN, isohydrogen cyanide, HNC, and HCO+, and so on. There are many more types, many more complicated molecules out there. And so how do now these observations look like? Yeah?
Quick question. So a lot of hydrocarbons.
Mhm.
Why? Why hydrocarbons and not something else? As an abundant, very abundant molecule.
It starts with neutral atomic, and hydrogen likes to connect with hydrogen, and then you end up with molecular hydrogen. Simply like that. Yeah.
Carbon's kind of the next one up. Helium doesn't like to form.
Yeah.
Carbon does. It's a carbon's next up the fusion chain.
Okay. Okay.
So yeah, how do we observe, or how do our observations now look like? A 3D cube in a way. So I uploaded this now into a representation tool. You see here now neutral atomic gas observed with MeerKAT, so the telescope in South Africa. This is the galaxy NGC 1512. You see a lot of spiral arms, huge spiral arms. And I want to remind you actually what we saw earlier with M83. The optical disk in this galaxy is actually inside of this ring, only inside of this ring. Also, the molecular gas is only in this little ring here. Everything else is neutral atomic hydrogen. So what do we do now with this kind of cube? So a cube has 3 axes, right? So we have the x-axis, y-axis, z-axis. The x and y-axis give you the indication of where your pixel are, so the pixel coordinates. The z-axis is frequency or wavelength. And so by summing up or integrating over the z-axis, we end up with an indication of how much gas there is. So this is called the moment zero map, integrated intensities. This means everything in these colors that are very yellow means there's a lot of gas. Everything that is more into this direction of the color bar is less gas. We can also look at the dynamics of this galaxy. So again, this is velocity, right? And so here is the center of the velocity in the frame of this galaxy. And the colors that represent here blue are blue shifted. So blue shifted velocities, red shifted velocities. So this means it's rotating, exactly. And you see very nicely in the center, it's very symmetric. So you assume that this rotates really nicely in circular motions. However, if you go out there, it's kind of messy. On the left, you see a spectra, which is extracted from a voxel, which is basically a pixel along, so multiple pixels along one z-axis. But then you end up with this spectra. And the moment 2 map here indicates the line width. And so the higher, the yellower the color, the broader your spectral width. And this indicates how turbulent your gas is. So here you see how much your gas have, how the gas moves, and how turbulent the gas is. Yeah.
Are those brighter areas where you have high level formation?
For the turbulence, you mean?
The areas that are very bright in your moment 0 and moment 2, are those where you're seeing high levels of star formation?
Yes. So
Yeah.
along the spiral arms, yes. And as actually, and I didn't show it here, it's a bummer, but this here and here, that's actually a companion galaxy. And it interacts with a dwarf galaxy, which is really interesting. So you can see this also here, the whole velocity field is a little bit disturbed because of that, because it's falling inside of this galaxy. Okay, and so now the multi-wavelength view of a spiral galaxy. just again, the electromagnetic spectrum from radio to all the way X-ray. We have atomic gas in the radio, molecular gas in the millimeter, infrared with James Webb, where we can observe dust. Dust is also very important for star formation because without dust, our gas cannot cool down. And if the gas is not cool enough, there will no stars. There will be no stars. And so in the visible, we see stars, something similar like our sun. And then in UV, for instance, with GALEX, a space telescope, we see very massive stars that radiate in the UV range. So massive, mostly young stars. And so just overlaying now some pictures. So this is now another galaxy, NGC 628, with HSD, JWSD. You see here also some bubbles. Those are structures of feedback. There you have the center, spiral arms. The molecular gas. You see the resolution is a little bit worse, but you still see a lot of emission along the spiral arms. And the neutral atomic gas, but I told you already it is more extended, so actually we need to zoom out again, captured with the very large array. So looking at, sorry.
So you showed the picture of the galaxy, the visible portion of it, and then outside is all that atomic gas. What percent of the overall mass of the galaxy is that atomic and addition? Yes.
Oh, I don't have that on top of my head, but it's more than half of it for sure.
Wow.
I was going to ask you a similar question because the initial thing for the Milky Way said that there are 100 billion stars and there's 1.5 trillion solar masses of mass, which is 15 times the average of the sun. You assume the sun is a larger than normal star with respect to the power of spot. There's got to be a lot of other stuff. And you mentioned the black hole was 4 million. It's like, well, that's not going to cut it. So my question would have been exactly how much mass you're talking about. It's got to be the majority, if not way majority. But
yeah. So it's so in the calculation, so that what I showed you was the neutral atomic gas, molecular gas, dust, everything all together. So summed up in a way, the 1.5 trillion solar masses. Yeah. Right, and so again, just a little bit of different view of the life cycle of a star now, which starts with a giant cloud, then some clumps begin to form within this cloud, then the regions begin to form then stars, and the stars then suck up the orbiting dust and gas material, and in the end we end up with a star and orbiting planets will form. So our planet, for instance. And so what do we learn from nearby galaxies now in a more simplistic way? And so along the spiral arms, we see a lot of star formation region. And along the dust lanes here, which are the bar lanes, we don't see a lot of star formation happening. So we don't see those pinkish colors, right? So the bar lanes lack stars. What we see, however, in the bar ends, so bar ends are just intersections between spiral arm and the bar, we have higher concentration of stars. And so additional factor is, or fact is that if we study nearby galaxies, is also in a way, looking into the past because they're so far away. And so they are in different stages of in their evolution. And so we can study then also different types of galaxies that are part in different evolution stages of their life. So whether they're starbursty, which means they have a burst of star formation, or if they are already quiescent galaxies where not a lot of star formation is happening anymore. And so gas in galaxies, a little bit of a other overview, just to bring my point across again in a different way. So neutral atomic gas is accreted from the intergalactic medium or surrounding satellite galaxies. So this is the bluish colors here in this schematic sketch here. And along its way, this gas will cool down, condense, form molecular clouds where H1, so the neutral atomic gas, is then converted to H2, the molecular gas. And so then further on, we are now somewhere here in the galaxy, stellar bars drive the gas even further into the center, and this leads to a further compression and conversion of gas. And then this will end up of an accumulation of molecular gas in the very center, can trigger enhanced star formation and feed the central supermassive black hole. And so now my work and contributions in a way, I will highlight one science result from one of my papers. And those will show observations of nearby galaxies with MeerKAT and ALMA. It's a more scientific plot that I will show you, but I will dissect it and will guide you through it. So what I want to do is I want to understand the balance between atomic and molecular gas in nearby galaxies, because as I showed you in the slide before, it's very important to know where this gas is transformed, because we also know that this has an impact on where stars are forming. And so we take high sensitive neutral atomic gas observations with MeerKAT, so that telescope in South Africa. And the same galaxies have been observed with ALMA, that telescope in Chile, from different collaborations, which I will talk later a little bit more. And so we studied the molecular gas fraction, RMOL, the balance between molecular and atomic gas. So this is the plot. I will break it down for you. On the y-axis, we see RMOL, which is molecular gas over neutral atomic gas. And what do we have here? RGAL R25. RGAL is the galactic centric radius. So if we would sit in the galaxy in the center, it's the radius outwards. And R25 is the optical radius of our galaxy. So this is just a normalization of the maximum extent of the galaxy to its optical radius. And the different colors, yeah, so this is now the extent, which is here represented now again as the H1, the neutral atomic gas contours, can be way larger than the optical radius that we already learned, right? Where at the very beginning I said for M83, it is 5 times larger than for the optical radius. And so the different colors represent different galaxies. So those are their telephone numbers. I'm not quite sure if you know any one of those. They're not that famous like the ones that I showed you before. You see now that there is not only one square, right? There are multiple squares. So what does this mean? Our observations look like that if we sampled them in a specific way. Again, this is this moment zero map that I showed you. So it shows you the amount of gas. Astronomers can choose any color map they want to choose. So you can choose, you can color your galaxies however you would like to color them. So again, here, however, is yellowish, means a lot of gas is there, and black color means not a lot of gas is there. Here, white is just nothing was detected, or we made a cut, like a signal to noise cut. And so each of these points here are actually individual points from here on this plot. So this is now NGC 1566. And so the balance that I'm interested in is reached if this is equals 1, right? So indicated with this line here. It's, however, at 0 because we are in the logarithmic scale. Astronomers like logarithmic scales. So just to show you that this is actually 1. And what we see, we fit here now over all these galaxies along the galactic-centric radius of fit, and see that this balance is crossed at this radius, at 0.36 to be exact, but approximately at 0.4 optical radii. That means that in a galaxy, on average, beyond 0.4 optical radii, so everything outside 0.4 is neutral atomic gas dominated, and everything inwards is molecular gas dominated. And at this balance, we see that the baryon mass budget is actually dominated by stars and not gas, which is very interesting as well. So just to highlight this now in a schematic way, again, an optical image from N83 now. Here, showing now the optical radius equals 1. I highlight there now 0.4, what we found here. So everything inside here is molecular dominated. Everything outside here is neutral atomic gas dominated. And this is the border of balance where R mol, so the molecular gas fraction, equals 1. And here we find 5 times more stars than gas. So gas means here molecular and neutral atomic gas together. And this changes, however, if you would look at different regions, right? Because we don't find any star formation happening anymore beyond the optical radius. We find it lesser and lesser in a way. So the overall scientific questions that I'm interested in are: how do galaxies evolve? How does cold gas get accreted, moved, and mixed through galaxies? What insights into the physics and chemistry of gas in galaxies can be derived from molecular line emission? What regulates star formation in galaxies? In what way is the formation of stars connected to the evolution of galaxies? And so all of this work and all of the work that I'm doing would not be possible with large collaborations. So those collaborations invest immense time to get a lot of time on telescopes. So what we usually do is we write proposals, which is like you have in a year about 5 to 10 proposal deadlines. You hope you get the data, then you reduce the data, image the data, and then can start this analysis. But it's really hard to get a lot of galaxies at different frequencies as well. So different telescopes, right? If you want to have a multi-wavelength overview, for instance. So again, astronomers like acronyms. I don't go into each of those, but Mongoose focuses on diffuse atomic gas, observing with the South African telescope MeerKAT, Nearby Galaxies as well. Phangs is a collaboration that I will talk about in a second. It focuses on diffuse atomic gas, dense molecular gas, stars, and star clusters, with the goal of having a multi-wavelength overview of more than 100 galaxies, which is a huge time investment. And this is a new survey focusing on the local group galaxies, diffuse atomic gas, really high resolution for atomic gas, I need to say, because it's still hard to get high resolution observations of diffuse atomic gas. Then 2 other collaborations which have different focuses. This one observes one particular galaxy, NGC 253, if you're familiar with that one. Really high resolution, a lot of molecules, completely different science, but I'm also interested in that. And GOALS observes a bunch of galaxies, but not those typical spiral galaxies that I showed you now, not these beautiful star-forming galaxies, but more extreme galaxies, actually. Galaxies that merge and collide, which is also very interesting to study. And so Phangs stands for Physics at High Angular Resolution in Nearby Galaxies. And so we observe around, here they are 90, but we are now around 100 galaxies actually, star-forming main sequence galaxies. That means those are galaxies that are typical spiral-ish galaxies with spiral arms here that form a lot of stars. And so what we do is, or what we want to do is to understand the baryon life cycle that I showed you earlier already, where we have different observations, different telescopes, where each of those observe and analyze different parts of this baryon life cycle. And ever since this is a large collaboration of more than a few 150 people now, and a lot of data, we dissect this in subgroups. And so I'm actually focusing on the diffuse atomic gas in this collaboration. And to jump back to this particular one, these two are pretty famous, right? I showed you M31, the Andromeda galaxy already, and M33. This is an survey. So now you see optical images with pointings of where the very large array, the VLA, looked at, of 6 local galaxies. So the star-forming galaxies here up, and some dwarf galaxies, IC10, NGC6822, IC1613, and WLM. And it's a really very, very large program. So you have different categories at a telescope, which is a small proposal, medium proposal, large proposal. And this category doesn't exist. It's a X large proposal. So, and it observes in all configurations. And in the end, if everything is processed, it will be able to capture neutral atomic gas at less than 20 parsec scales, which is really incredible. Just to show you, a first survey paper was published 1 month ago with a first data release of the 100 parsec scales, where you can see already substructures here. And this is really beautiful and nice to see this now also in neutral atomic gas. And it's nice to have that in such a high resolution where then almost can match it with ALMA to then observe it also with molecular gas and do the molecular gas fraction actually on similar scales. And this is really incredible because most of the neutral atomic gas surveys had resolutions of kiloparsec scales, a few kiloparsec scales actually. So now we are able to resolve substructures and also here in the arm and the disc, some individual filaments even, which is incredible. And so I leave you with my summary and this one little research highlight that was just one result of many from this paper. And if you have more questions or any things that you want to talk with me about, you can reach me under this email or website where I also have some of my contacts available. So yeah, with that, I'm happy to take some questions. Yeah.
Got one. Coming back a little bit to the mass, especially in light of your 0.4 optical resolve, there's a couple of things I noticed. One was you mentioned that the radio footprint of the galaxy was much bigger than the optical one, but your graph only showed like 10% beyond the optical size. So maybe that was just sensitivity or something like that.
You meant
This, you know, when you had your log of the ratio of carbon monoxide to neutral hydrogen with
it's just
with the distance ratio. Or maybe it was.
It's very slow. I know what you mean.
Well, you can take that. That's not my main question, actually. Yeah, that was it right there. Yeah, no, that one's fine.
Okay, that's it. Yeah.
Yeah, you know, your R galaxy over R25 only goes up to about 10% more than, 1.1, as opposed to what it seemed like you were saying it was much more than that. And maybe that's just an observational effect. The horizontal axis.
Here, about one, you mean?
Yeah, so one, it would be like what you're looking at was I was expecting R gal over R25 to go based on the pictures you were showing to be like 3 or 4, up to 3 or 4. Our galaxy was much larger, could be much larger than R25.
Right. Yes. Yeah. But this is first, it's normalized, right, by something. So you will end up with 1 anyways.
Why is that? Because R25
changes with each galaxy.
Yes, but I thought that you were showing pictures of the same galaxy where the R galaxy, the radius of, the little cartoon in the middle, I thought was the optical part, and the other part was the other part. And so I was expecting just this ratio of this number to this number to be considerably more than 1. And so maybe I misinterpreted what you meant. And maybe it's just a sensitivity thing. That wasn't the main part of the question.
Yeah, no. I get where, no, I get now the questions. I'm sorry. The thing is, what we also have a limiting factor is actually our ALMA observations, so the molecular gas observations, which are not entirely covering everything of the galaxy. This is one limiting factor because it's very difficult to observe molecular gas at the edges of a galaxy where you would need a long of integration times to get that.
Okay.
Which is the next part of my research as well, to go into very so-called low metallicity environments. Okay. Yeah, so this is why we are in a way only looking at this part here, right?
Yeah, okay, yeah. So that's fine. So that the second part of my question, and this is, forgive me for going back to the little mass thing, but you said the baryon mass, the distribution was dominated by stars at less than 0.36, right?
Yeah.
You had 5x the distribution. And now I'm a little bit more confused about the total mass, unless perhaps the total mass of the galaxy is mostly outside. We said earlier that star mass didn't dominate a galaxy. And this
is, however, in the very center. If you look at like the neutral atomic gas distribution, right? This is huge. It's a lot of mass out there. So if you go a little bit out here only, you have way less stars. And so there, the dominant factor would be neutral atomic gas.
But the total mass of the whole galaxy
would be everything included.
Is much more outside that region.
Yeah, outside the 0.4 for sure.
Okay.
Yeah.
Okay. All right. And I guess one more thing, well, I'm sorry to monopolize, but that you said the ratio of the carbon monoxide to neutral hydrogen was 10 to the -4. Is that a modeled result or an experimented result? Or?
It's from observations from our own galaxy, right?
It's much easier to do that.
Yeah.
Okay. All right. Thank you.
Distribution of like how it varies.
Well, right.
Right. It varies. It varies quite a lot.
Okay.
So it's actually one of the most discussed subjects within the extragalactic community, how to pinpoint this so-called alpha CO factor, which is the factor that you use to convert CO to H2. And what we know is that it depends on metallicity. So everything that is heavier than helium. And so it will vary with galaxy as well, of course. And so in this study that I showed you now, we actually account for that, where we used for each galaxy our own conversion factor that is metallicity dependent.
See, thank you.
Questions? Here, would you take this?
Where does the Earth fall in this, in the Milky Way, in this star forming radius? Or can we even know that because we're in it?
Oh, I mean, like everything that we, that would be very, the artistic. Do you mean like where we fall here, like?
So
it's
I
like
see
in
where
the-
the Earth is,
Yes.
but you said there's this area that where there dense molecular gas and diffuse gas in that ring is where the stars are forming predominantly.
Right.
Where is that ring in the Milky Way?
So that I would assume, I didn't do it, I would assume it would be exactly, so we would be inside of the more molecular dominated region.
So
yeah.
we're in the high molecular density gas, whatever.
Yes, yes.
Okay.
And so we are
That was
also
my mundane
in a spiral arm, right? So where we have a lot of star formation happening. So
Questions? I've got one for you. How does dark matter, dark energy fit all into all your equation? I mean, you don't know what it is, so how does it fit?
yeah. So I didn't show you anything about the kinematics, right? I was thinking about showing a result about that as well. But what I'm also interested in is, wait. This here, right? The kinematics of a galaxy. And so especially the rotation curves, where people, because of the rotation curves, figure out, okay, there must be something more out there that keeps everything together, right? Which is dark matter. And so whenever we model those rotation curves, we need to account for dark matter, yes. But in the very center of a galaxy, so the part where molecular gas dominates, we don't believe that dark matter is so important. In fact, some people say we can neglect it because it's not that important in the central part of a galaxy.
So in the outer part, the assumption though is that dark matter is evenly distributed, or?
Yeah, as far that I know, yes. So you have, I would assume here you have evenly distributed dark matter, yeah.
It makes it work. Any other questions? Questions? Is that it? Excellent. All right. Well, thanks so much for coming here. I know you were in the neighborhood, so you're right down the street here at NRAS, but that's fantastic. I've been telling everybody you came all the way from Austria
Yeah.
just for this, but nobody ever believes me anyway. Don't worry about it. So for coming here, we have this fantastic, the coveted Cass coffee cup
Nice.
that you can bring back with you, and we appreciate it. This was great. This was very good. It was understood for guys like me. I got it. Kind of makes sense. You see this mother folks in the room who really know a lot, and it hopefully was good for them too. And but it was great. This was a lot of fun.
Thank
Appreciate
you.
it. Thanks so much.
Thank you.
Okay.